Sociedad Astronómica UADY presenta La Tortuga Cósmica, un espacio sobre el espacio para niños y jóvenes.
Hey Astro viewers, welcome to another edition of Tortuga Cósmica. We are members of the Astronomical Society of UADY. My name is Janine and the name of my colleague is Brisa. And today we have with us the Dr. Jocelyn Bell Burnell. And she is the person who discovered the first observational evidence of a pulsar when she was a PhD student. She did her PhD degree in Cambridge University, and now she's an astrophysicist that works in Oxford University. So now we are honored to come with her presence today. Thank you, Doctor, for answering us. we in the appreciation of the knowledge that you have in this field, we would like to make a little interview.
Excellent.
Yes.
Thank you.
So welcome, Dr. Bell. We thank you for taking your time to speak with us. And before starting the interview, we would like to inform to all the viewers here that you worked in radioastronomy in the very first years of this area in astrophysics. Radioastronomy born in 40s, and you worked in radioastronomy in the 60s, right?
Yes.
So a lot of people here don't know what is radioastronomy. They think astronomy and things in a telescope that see visible light, but they don't know that it exists radioastronomy. So could you explain what is this?
Yes. In fact, today we do astronomy right across the spectrum, the electromagnetic spectrum. There's radio astronomy, millimeter wave, infrared, optical, ultraviolet, X-ray, gamma ray, the whole lot. And Mexico increasingly is getting some of these newer wavelengths. You've got a number of new telescopes building. You've got the large millimeter telescope that's going to the state. That's working between radio and infrared, observing the universe in those wavelengths. You've got HAWK, High Altitude Water Cherenkov Gamma Ray Observatory, Sierra Negra. That's looking at very high energy, very, very short wavelength gamma rays. In Bahia, California, at the National Astronomical Observatory, there's a big 6.5 meter telescope building, I believe, and it's going to do infrared and optical. And you've got a number of smaller optical telescopes as well. You don't have much radio as far as I can see, but radio is just like long wavelength infrared, put it that way. It's part of the electromagnetic spectrum. And we now know that you can observe the universe in all those wavelengths, although you tend to see different things at the different wavelengths. So in radio astronomy, you see things like quasars. You can see molecular gas, hot molecular gas, and also pulsars.
Okay, so radio astronomy is a very young area of astrophysics, as Grisa said. How did you get interested in this one? Like it was just developing when you started studying astronomy. How did you choose radio instead of the others?
I chose radio astronomy quite early, probably about age 14. As soon as we started doing physics in high school, which was about age 12, it was clear I was good at physics. It was my best subject and I liked it. And so I was thinking, okay, suppose when I'm a student, I do a physics degree. What am I going to do after that? Because there are many, many things you can do with a physics degree. And I became interested in astronomy through reading a book that my father brought home from the public library. But of course, I first thought about optical astronomy and then thought, oh dear, I need my sleep. I like my bed. I do not want to work at night. To be an optical astronomer. But radio astronomy, you can do day and night because the sun does not blind you in the day at radio wavelengths. And so usually you work during the day and sleep at night. And that's good.
Yeah, that's a really good answer to be a radio astronomer, right? We love sleep. Also, me too. I also work in radio, but I'm in a master's degree, so I'm a little baby here. Is the best part. I read that you built a radio telescope, right?
Mm-hmm. Yes. In Britain, the PhD program is 3 years, and I spent 2 years building the radio telescope.
Oh my gosh.
Oh my gosh.
It was a very simple kind of radio telescope, although very large. So it wasn't complicated to build, it was just big. So it had, for instance, thousands of posts that we had to hammer into the ground.
Yeah. Do you use this radio telescope that you built for your PhD degree, or you use another telescope?
No, it was the telescope that I built was the one that I used for my PhD. Yes, that's right.
Oh, that's really great. Yeah. So you start studying quasars, so you have a transition in different lines of investigation. Then you discover the pulsars, and you have worked also with binary stars, if I understand. Okay. So could you tell us what is your current field of research now?
Right. Well, I have worked at many wavelengths. I started in radio astronomy. I then moved to the other end of the spectrum to gamma ray astronomy. And then I gradually worked down the spectrum to X-ray and then infrared. So I've covered many wavelengths. And these days I will work at whatever wavelength is best for the problem. So today I am particularly interested in neutron stars, which show us pulsars and X-ray astronomy. I am also interested in transient events, things that brighten up and die. So particularly at the moment, fast radio bursts, which look like one pulse from a pulsar. But then you realize it's very, very distant, way, way beyond our galaxy in some other galaxy. And we couldn't see a pulsar at that distance. So we don't know what these fast radio bursts are yet, but they're very intriguing.
So you have been working in almost all the wavelengths, no? As you said, what is the principal difference among all of them?
You see different objects at the different wave bands, and you use different equipment. For example, if you study X-ray astronomy, you have to get your telescope up above the atmosphere because the Earth's atmosphere cuts out the X-rays. So you're using a satellite. So for gamma rays, you use satellites or maybe balloons. For infrared, you need to be on top of a high mountain, and also for millimeter, so that it's dry. Or you could be in a satellite, but a mountain is cheaper, less expensive. So you see different objects, you use different kinds of telescopes in different places. So lots of interest.
Yeah, it is very interesting.
So you work in different wavelengths, so you are the best person to tell us why it's important to make a complete study in all the wavelengths that you can observe for the objects. So why is important this?
Yes, that's very helpful, because if you study something in a narrow wave band, you perhaps have a picture of what it is. and then you make a prediction about what it will be like over here. So maybe you observe it in radio and you say, if my picture, if my model is correct, then we should see it in the infrared. Go look in the infrared. Maybe you do see it, maybe you don't. Maybe your picture is wrong, maybe your picture is right.
Yeah.
So
Yeah.
I want to add something. I'm not sure because I'm not an astronomer, but as I understand, with the black hole that we observed the last year, they work with all the wavelengths, no?
This one?
Yeah, actually, that so they can obtain a whole picture, no? So that's more or less what you're explaining.
Yes, although I think that was mainly radio waves, that one, but with
Okay.
many different radio telescopes working together. Yeah. But
Okay.
yes, you need many wavelengths to understand your object properly.
Yeah, that's very interesting because you can see some specific thing in an object with a wavelength, and then the other wavelength completes that knowledge that you are having. No?
Yes, or contradicts it. Maybe you're wrong. So maybe it's good, maybe it's not good.
Well, yeah, that's right. Wow.
Yeah.
So you mentioned before that one object that you can observe is a pulsar, and well, that's one of the one of the biggest discoveries made in the physics, no? So what is it? And could you explain more about this object and its discovery?
Right, well, a pulsar is also called a neutron star. It's a star that's very rich in neutrons. It's not pure neutrons, there are other things as well, but there are a lot of neutrons. So they're sometimes called neutron stars. They have a radius of about 10 kilometers, only 10 kilometers. But they have a mass about 1 1/4, 1 1/3 times the mass of the sun. So they are very, very dense. So for instance, if you take a cubic centimeter of this star, it weighs the same as all the people in the world.
Wow.
The whole population of the world weighs the same as this cubic centimeter of star or neutron star. So the physics is very extreme and interesting for that as well. Yeah. So that's what we now understand pulsars to be. They are spinning and they have a magnetic field. So if this is the magnetic field and this is the spin axis, it goes around like this, the magnetic field.
Yeah.
And we believe the radio beam comes out from the north and south magnetic poles. As it goes round, you see a radio beam and see a radio beam and see a radio beam. It goes much faster than I can do.
Yeah. So how do you discover it?
By
because
accident.
You are the one. By accident, okay.
I wonder if you know the phrase imposter syndrome. Have you heard?
Yeah, more or less. I've read about it. Like somebody doesn't recognize their achievements, no?
Yes, that's right. So I went from Scotland, which is a long way north, to Cambridge, which is a big, big, prestigious place. And everybody there was very clever. I knew I was clever. And I thought, they've made a mistake. They're going to throw me out. We have a name for this in Britain, Imposter Syndrome. And in a bad case, the student will say, I'd better leave before they throw me out. And the student goes. Well, when I came to Cambridge, I thought, I'm not clever enough. They've made a mistake. They're going to throw me out. But until they throw me out, I will work my very, very hardest so that when they throw me out, I will not have a guilty conscience. I will know I've done my best and I just wasn't clever enough. So I was working very, very hard, being extremely thorough, very careful. And that's how I noticed the pulsars. So it's due to what we call imposter syndrome.
Okay. So I was reading your paper and I see a graph that where you detect the pulse. So I have curious there because when I read also the paper of Rudolf Weber, one of the fathers of radioastronomy, in some place in the paper he says that he detects some signals, not like pulse, but some signals that it associate to contamination of like noise or something like that. So when you see the pulses, how do you distinguish that the peaks that you see in the paper was an astronomical source, an astronomical object, and not another source of contamination? So how did you know that?
Because whenever it came back, whenever it repeated, it was 23 hours, 56 minutes later.
Okay.
Now, radio telescopes pick up a lot of interference. For instance, cars, cars that are badly suppressed can give bursts of radio emission, which a radio telescope will pick up. All sorts of things that give sparks, give radio waves. But things produced by people, if they have any pattern, it's 24 hours because we work on a 24-hour day.
Okay.
But a 23-hour, 56-minute day. And that's the sidereal day, the time it takes for a star to be in a particular spot, go down, set, come round the back of the Earth, rise again, and get back to that spot. 23 hours, 56 minutes. And so this curious signal was keeping this 23-hour, 56-minute day. So it had to be something up in the stars, not humans.
And here I have another question that comes to my mind now. Okay. Do you think that maybe someone had a record of these pulses before and they don't catch attention on this? Or
there are some interesting stories. The most amazing one is actually about optical astronomy.
Okay.
There's an observatory in Texas in the United States, which has an open day once a month. And back in 1957, long time ago, 1957, in late summer, it was the open night at the observatory, and members of the public came in and looked through the telescope.
Okay.
And the telescope was set looking at the Crab Nebula.
Okay.
They knew there was a curious star in the center of the Crab Nebula, the remains of the star that exploded to give the nebula. And people stepped up to the telescope and looked at the light from this star. And a young woman stepped up to the telescope and said, "That star's flashing."
Wow.
And the night assistant talked about atmospheric scintillation, turbulence, and she said, "No, I know about that. My job is to fly newly built aeroplanes from the manufacturer to the customer. I fly at night. I know about scintillation, the twinkling of the stars. That star is flashing. And nobody followed up on her remarks.
Wow.
Had they would have discovered the Crab pulsar in 1957. It goes quite fast. It goes 30 times a second. But some people, especially young women, can see flashes at that rate. Canada used to have its mains power supply at 30 hertz. And some people could see it because the lights flashed, the television flashed at 30 hertz. So some people can see things that fast.
Wow.
So I think she saw it, but nobody took any notice.
Wow, that's a very interesting story.
Yeah, it happened.
How many things we can discover if we listen to old people.
Yeah, that we.
Crazy ones, yes.
Uh-huh. At
Yeah.
that time, you don't pay that much attention, but after sometimes some discoveries, you see that it was an important apportation that nobody wanted to take in account.
Yeah, yeah.
So when you were studying your PhD, I believe, well, I'm not sure, but I believe that there weren't many women in the area. No, now we see a lot of girls and young women interested in astrophysics. How do you feel about that?
I think it's great. We see more women in many science areas now in Britain, and we have a scheme. Let me start that again. The government bodies that give us money for research now insist that there have to be a good number of women working in a research field. Yep, it's called Athena Swan. It's one of the things I helped set up. So, and when funding bodies insist on there being a good number of women, everybody has to pay attention.
Yeah, actually, you won the Breakthrough Prize in 2018, no? And you donated the money to give scholarships to women, to minorities, no, different ethnicities, so they can also have the opportunity to study in this area.
Yes. Yes,
Wow.
the first people will be starting in September. And I think they will be announcing the names very, very soon. So we'll hear who has got these fellowships and how many of them there are, which would be lovely.
I really liked when you said that about the impostor syndrome, that you said, well, I'm not giving up until they kick me out, no? So I think many women in science, they start and they feel that, no, like I'm not good enough. I'm not gonna make it. I don't understand. I can't do it, no, and they just quit.
Yes.
So I think that way of thinking, like I will give my best, is very important, and
Yeah.
also very admirable to have a role model like you, that you have achieved a lot of things, because I think everybody has that kind of doubts, like I'm not good enough, no? But that way of thinking, of saying, okay, I might be not good enough, but I will try and I will do my best, is very important. So I really admire that.
I think that's especially true for women. I think some men will feel imposter syndrome, but some will not. But women often do. Yeah.
Yeah, that's true. I have a question that is about, because like I said before, now I'm studying in radio, so I have so many tools to study this. But your time when you was a PhD student, I think that it was harder to obtain the same physical information from a source, right? For example, now we have softwares like CASA that is used for the most iconic radio interferometers like ALMA, BLA. But when you were studying, you have to analyze a long piece of paper. I don't know how was the instrumentation, so I'm very curious in this. Can you tell me what was your experience then? What improvements you see in the technology that we have now?
Mm-hmm. Mm-hmm. So at the time I did my PhD, University of Cambridge had one computer.
Okay.
And it had less memory than your laptop.
Oh my gosh.
And it took up a whole room because we didn't have transistors. It was using tubes or valves, so it was very, very big. And very few people could get time on it. And we did not have time on it. So that's why my data came out on paper, rolls and rolls and rolls of paper. Now we have computers and telescopes become more automatic. And one of the things that interests me is a new telescope building in Chile, which is now called the Vera Rubin telescope, called the LSST, the Large Synoptic Survey Telescope, but it's renamed after Vera Rubin. And it is going to be looking for transient events, things that flare up and die. And there will be a huge number of them, millions every night. And so you need the analysis done by computers, not by graduate students. And it's going to be interesting. How do you program a computer to look for something that you do not know exists?
Yeah, that's right.
If we had used computer analysis on my data, would the computer have detected pulsars? I think it would have said interference. There's lots of interference. So, yeah.
Yeah.
So it's an interesting question.
Yeah, it's I always have this curious. Thank you for answering this. I read that when you was studying the PhD. I don't know if I'm wrong, but you were studying quasars, right?
Yes. Yeah.
And the observations that you were made in that moment were for quasars, and then you discovered the pulsars, or how was that?
Yeah, that's right. Yes. The project was to find more quasars. At the time when I started, there were only about 20 quasars known. It's been recently discovered that they were very, very distant. So they must be incredibly strong. And it would be really good to have some more. And my particular PhD project, and that's what my PhD thesis was on, the pulsars went in an appendix.
Okay.
The main thesis was about finding more quasars. And I found about 180 more. So by the end, we had 200, having started with 20. So that's a good size sample. So yes, the thesis had to be on the quasars because my advisor said it was too late to change the type of thesis.
Okay.
Pulsars were in the appendix.
Okay, so when you detect the pulses, you were observing some quasar,
Yes.
right? Oh, that's interesting.
Well, put differently, the way I was finding the quasars was looking for things whose brightness changed quite fast.
Okay.
It's called scintillation.
Yeah.
And the radio scintillation is caused by the solar wind that comes out from the sun.
Wow.
It makes compact objects twinkle, scintillate. So I was looking for objects that changed their brightness fast, rapidly,
Yeah.
and how the pulsars came about.
Wow, that's interesting. Yeah,
Yeah, you can.
it's incredible.
Yeah, you can see very interesting things in astrophysics. No, like I remember that we had. Well, I didn't have it because I was in another. I don't know. in high school, they offered that subject, astrophysics, like an introduction to astrophysics. But it was in high school in the time of my parents. So when I was going to study, when I wanted to choose astrophysics, I didn't have the opportunity, you know. So I studied another different career, but I really like this field. It's very interesting. You always discover something different, or you can, as you said, not you can contradict something that was in the general thinking, so you can prove new things.
Yeah.
It's a science that evolves day to day. Sorry.
What is your major, Yanni?
I'm an architect and I'm studying the master in engineering.
My father was an architect.
Wow. Yeah. Well, as an architect, you can also get inspired by the universe. So with so many things. And
My father designed a planetarium.
oh my
Whoa!
God!
But they had great trouble with it because the builder could not get the shape of the dome right.
Oh,
Wow. In your city, he built the planetarium, or in another city?
Nearby, in the nearest big city. We lived in the country.
Mm-hmm.
It's in a city called Armagh, Armagh, Irish name.
Ah, yeah. Wow. So, well, we are very grateful to have you here. Risa, I don't know if you want to ask something else. We have like 3 minutes left. So.
Oh my gosh. Okay. Well, there's a lot of young women and girls that are interested in astrophysics. I was one of them when I was a little girl. So I really love your job, and you're an inspiration for me because you work in radio. That's something that means so much for me, right? But there are more girls and women that are thinking, can I study this? Cannot. So what could you say to all of them?
I think science in general is a great subject. Astrophysics, astronomy is hugely exciting.
Yeah.
You'll need some physics. It's a good idea to have some physics, but a career in astronomy or astrophysics is fantastic. It's so exciting. And in Mexico, with many new telescopes coming online, there are all sorts of interesting opportunities coming up. So if a young woman is interested, I would say, go for it, do your best.
Thank you so much. Really, it was an honor to meet you virtually, but meet you. So thank you so much for being with us today.
Yeah, thank you so much for taking the time also, for giving us a space in your schedule.
It's been fun for me. So thank you to both of you as well for the work you've done already and the work you've yet to do.
Búscanos en redes sociales como Sociedad Astronómica UADY.